My name is Nolan Serafin. I'm the team leader for the electronic cornhole scoring system senior design project. Today I'm accompanied by Alex Miracle, Corey Wagner, and Greg Goldstein. And our team is advised by our advisor, Dr. Vijay Devabhaktuni, our co-advisor, Dr. Devinder Kaur, and our grad student mentor, Praveen Damachal. Today, the topics that we're going to be covering, first off, the cornhole instructional walkthrough. We're going to give you a basic layout of how the game is actually played, the current limitations to the scoring system, benefits of the electronic system which we are going to implement, the design specifications, how we're going to go about completing our project, a quick demonstration on the document viewer, the mechanical aspects and additions that we're going to make to the cornhole board so that way this will work properly, problems encountered in our design, implementation, testing, and verification, and also a conclusion to recap what we talked about here today.
First thing we talk about is the gameplay itself, just so you all kind of have a background if you don't know how cornhole is actually played. It's fairly simple. It requires 4 players divided into 2 even teams. Between those 2 players are cornhole boards. They're spaced roughly 27 feet apart, give or take. Each team has 1 member on each side of the playing field. They're generally spaced across from each other, so if it's myself and Nolan and Corey and Greg are on another team, we would be facing each other. The game is played with beanbags, simple enough. Each team gets 4 of each, and the objective is to score 21 points. Points are accumulated by throwing the bag at the opposing side's cornhole board. If it lands on the board, you get a single point, which is known as an ace point. Or if you land in the cornhole itself, it's 3 points. Anything outside of that is just 0, doesn't count for anything. Next slide. I'm just going to run through a basic example to go through the scoring system. So you have the board here set up just like so. If team 1 would throw a cornhole bag, or a bean bag, it would land on the board. Then team 2 tosses next. Team 1 then goes again. And then team 2 then rethrows their second bag into the cornhole. Play continues until both team members have thrown their 4 bags. Once that's done, the score is then tallied. So right here you see 2 on the board, 1 in. Score is also deducted from each other. So what I mean by that is that by having 1 bag from each team on the board, it zeroes each other out. By having 1 in the hole, team 2 walks away from this round with 3 points. After each round, the score stays, I guess, stagnant. So then the next round continues with 3-0 and so forth.
All right, current limitations. The current limitations of cornhole is that there's really no scoring system that's in place. This is a really social game. People like to play for fun. You'll see a lot of tailgating or graduation parties. The issue comes into play that while you're playing, you're socializing, you're a little bit more focused on having fun, and teams tend to forget scores. So what we want to do is implement something that's going to help us with that. A lot of times the teams will get into arguments when they forget scores and try to figure out not only which team's winning, but what the exact score is, and that can cause some real issues, and we want people to just be able to focus on having fun with this game. So we're implementing an electronic scoring system. We're going to make it semi-automatic. It's got 2 parts to it. One part is the automatic scoring for the cornholes or the 3-pointers, and the other part would be the single points or the aces. We're going to implement push buttons in order to update the LCD screen appropriately. What we're hoping to do with this is to have less confusion. Teams will always agree the LCD should be correct, and they'll be able to say, okay, well, this is the team that's winning, and this is how many points we have. We're also going to have it so once we've reached 21 points, or whichever team reaches 21, so we'll say game over, you win, and the scoreboard will reset so that another game may begin playing. And the way we're going about doing this, at least for the automatic portion, we looked into a couple different electronic options to do the automatic scoring, one of which is the RFID, which you see here. Some of the other options we looked into were pressure sensors and photo detectors. There were some issues with those other 2 options, the main one being the inability to differentiate between 2 teams. For instance, if we were to use a pressure sensor, the pressure sensor would go underneath the cornhole board. When the bag landed on it, it would update the LCD. The problem is you can't differentiate between the 2 teams. One way we might be able to do that would be to have different weighted bags, but that would hurt the integrity of the game. Then one team might have an unfair advantage being able to throw a lighter bag, and so on and so forth. Also with the photo detectors, very similar. The LCD would be updated as the bag passed through, but we wouldn't be able to tell which team scored the points. So we decided to go with RFID. Now the way we're going to implement into this end of the board is we're building a ramp underneath the hole, and the sensor will be underneath that ramp. We're going to take our tags that look like this. They give out a specific frequency that the sensor will read. Ours is 13.56 megahertz. We will place these inside the bags. That way, as the bag goes in and slides over the sensor will read the unique identifier that's associated with each tag, and then our control device will be coded in a way that that unique identifier can be differentiated between the two different teams, and the LCD can be adjusted appropriately. Now, the way we want to go about doing this to make this as accurate as possible, rather than putting one tag in the bag, which would be a little bit more efficient, but we might have some issues. You never know how the bag's going to land on that ramp. It could land a number of ways, and if we have the tag placed, say it's in the top corner and the bag lands like this, we don't want there to be accuracy issues with reading that tag. So what we plan on doing is putting multiple tags inside of one bag and obviously adjusting the weight accordingly. And then what we'll be able to do is make sure that there's always an accurate adjusted score as the bag passes through, and we'll adjust our code appropriately for that. Now, for the up, down, and reset buttons that we plan on implementing, we have a couple of different ways that we can go about this with our control device. We could use digital inputs. We could use our digital inputs for each button, but we felt that that would be a little bit inefficient, so we looked for other ways to go about this. What we ended up doing is using one analog input for each of our buttons. This illustration kind of shows us how we went about doing that. As you can see, we're only using A0, our analog input, and S1 through S4 would be our different buttons. Now, each one of those buttons has a different resistance value associated with it. For instance, if S4 is pressed, only R5 resistance will be associated with that. If S3 is pressed, R1 and R6, and so on. So what that's doing is these analog inputs are getting readings from 0 to 5 volts. And that's being broken into the control device is actually seeing a number from 0 to 1023. So depending, for instance, if we were to press S4, it might give a reading to the control device of, let's say, 700. Now, because of the different resistance value for S3, it will get a different reading. It'll get more of like a 400 or 500. So we found out those values depending on our resistors and coded our control device in order to take the individual buttons, see those different readings, and update the score appropriately so that we can minimize the amount of inputs that we're using.
So the control device that he mentioned that we're using for our project is the Arduino Uno. We decided to do this because it is a low-power device. It takes 7 to 12 volts for the input. And as you can see on the top row, we have the digital input and outputs. And bottom right, we have the analog input and output. And then at the bottom row, you see power and grounding. So the nice thing about this, it uses C# programming, which we're familiar with based on our courses here at UT. And it's relatively inexpensive considering that it comes with the microcontroller and easily adaptable pins that we can use jumper wires to connect to the breadboard. And the nice thing about this, you can write the code, upload it to the Arduino, and then test it almost immediately. Another nice feature about this is the voltage regulation capability. So if we're supplying 12 volts to our Arduino, if we need, say, 3.3 volts, which we use for the RFID sensor, or if we need 5 volts for the LCD display, we're able to have both of those. And no soldering, so it's easy to interface with the breadboard. And this is the liquid crystal display that we're going to use to display the score during the game. The liquid crystal display, it's a 2x16, 2 rows, and 16 characters per row. We'll have one team for each row, and it's going to be interfaced with the Arduino Uno using the input-output on the top row.
Since we have two separate boards, the primary and the secondary board, we had to figure out how we're going to send the data from the secondary board to the primary board. Now, we didn't want to use a wire because that would just be very, it could cause tripping hazard, be very inconvenient. So the obvious choice for us was to make it wireless. So what we decided to use was the XB. We decided to use this because it can transfer up to about 100 feet. It's only about 27 feet apart, so it's definitely far enough range. And it's very easily interfaced with the Arduino. So what we did was we bought a shield to go with it. That way the XB would plug right into it. This eliminates the process of us trying to figure out what pins go to where on the Arduino, and we can actually focus most of our time on the coding part of it. So that's why we did the shield and the XB. It's just very easily interfaced with the Arduino. So Now for the power, the Arduino can handle about 7 to 12 volts, but the 7-volt part of it wouldn't be able to output enough volts in the 5-volt output, so our switches wouldn't update because it just wouldn't have enough power to power our whole system. So we decided to use a 12-volt battery, and now we had to do, to make it portable, we had to get a small enough battery but have enough voltage push out. So we used this universal battery, which is about 2.8 pounds, so it doesn't add that much weight to our system. It's still easily portable, and the size is about the third of the size of a car battery, so it's very easily implemented underneath the board. And if it ever needs to be recharged, we can use a trickle charger, and it charges it back up to full power, so it can be easily reused multiple times.
We're just going to go over a quick scoring demonstration. We have a tag here, so will be Team 1's tag, and then this RFID tag will be Team 2's tag. This is the system as is. As you can see the LED, you have Team 1. So if Team 1 would score a cornhole, the RFID tag would scan, you would see 3 points. If Team 2 would then go, it would go to 0, and then if they'd say score again, it would implement 3. We also have push buttons. So if Team 1 scores, it deducts. Or if Team 2 would then score a single, or say Team 1 then would score another cornhole, it removes the single point and then adds the 2 points as well. So that's just a quick demonstration on how our system works so far.
Now this game is usually played like it's a fair weather game, so normally it's not played in extreme conditions, but we figured we'd have to test it anyways just in case somebody would want to play in very hot or very cold conditions. So what we're going to do is we're going to test it in about a 100-degree environment, and then we're just going to make sure that our appliances aren't going to overheat, and if they don't and the system keeps running, that's the game plan. And we think it will, but we're going to test that in the near future. Also, we're going to put it in a cold, about 30 to 40-degree environment, just to make sure the battery's not going to lose charge, because batteries easily lose charge in cold weather. We just want to make sure that it's going to power the system, the game can be successfully played. Also, since the weather is really unpredictable, if it would start to rain, we want to have at least some cover on it so that electronics don't get wet, because obviously electronics and water do not mix. So I'm going to go talk about the mechanical aspect of it. Now the top right is going to be how a normal board's going to look like underneath. What we did was we put a backboard on that, where we're going to install a shelf to put all of our electronics on. As you can see in the bottom left, we're going to build off of that. You can see the ramp also. As Corey explained earlier, the RFID is going to be underneath that. It's a plexiglass ramp, so it can easily see through that. So when the bag comes down, it's going to hit the ramp, it's going to slowly go across that, and it's going to scan that, and it's going to update the LCD. Now the LCD is going to be located on the primary board. As you can see in the top right picture, it's at the very top, so it's easily seen by the users. Also, the up and down push buttons are going to be up there for each team, and a reset button. And it's up there because it can be easily reachable, so it's very user friendly, and you can see the score. So that's a great spot to put that. Now on the bottom right, you can see the shelf, how we're going to build it off of the backboard. The shelf is going to be where we put the battery and all the electronics, and it's going to be completely enclosed, so the rain cannot get to it, and that's how the mechanical aspect of that's going to go.
So for problems encountered going through this process, one of the major things that was difficult for us was the programming part of it. All of us are electrical engineers, so we had to do a lot of initial research and see how we could implement this project and get it so that the scoring system actually works the way that we want it to. And we had to start from the ground up, just do enough research so we could find out how the RFID detects the actual cards, and then how we can have the Arduino read it and get the unique identifiers, and then build up from there, put in the mechanics of the game, how the scoring's done, and make sure everything scores correctly. Another major issue that we had was integrating the XB and the RFID on the secondary board, which transmits to the primary board, and the score is updated on the LCD. The main issue that we had with the RFID, it's a serial peripheral interface, and the XB being a universal synchronous, asynchronous receiver and transmitter. The SPI was used to talk to devices in the same circuit, and the USART needs some sort of control device, so that way the RFID can communicate to the wireless transmitter. And to do that, we ended up implementing another control device on the secondary board, so that way it could do that correctly. And lastly, another issue that we're working through is the board and bag modification, so that way when we're actually testing and demonstrating this, the bags are being scanned correctly, and also that the board is modified and we have the ramp at a correct angle, so that way the bag doesn't slide down too fast and the tags aren't being sensed, or the ramp is too shallow and the bags do not slide and they pile up. And so for a conclusion, what we discussed today, the limits of the current scoring system, how it's currently being done, and what can be improved on that. Our electronic solution by implementing the scoring system, so that way players can focus more on the social aspect and focus on having fun and playing the game than focusing on the score. The technical aspects as far as how we're going to do this, all the different components involved, and also the mechanical changes that will be made to the board, so that way this can be implemented.
Real quick before we go into the questions, we just wanted to thank both of our professors. We've had a lot of help from both VJ and Professor Carr have helped us tremendously, as well as our grad student mentors. Been a huge help, and in the last 2 semesters, Professor Sturt been helping us out a lot. We really appreciate all the pushing we've gotten to get all this done and get it done right. So we just want to say thank you for that real quick.
So we'll go ahead and open the floor for questions.
You guys didn't bring up in scoring the if you go over 21 rule. Are you implementing that?
That'll be implemented in the code.
Do you want to explain it so everybody else understands what I'm talking
In the
about?
game of Cornhole, if a team goes over 21 points, they are then technically reset at the end of that round back to either 11 or 13. It kind of depends, like a house rules kind of thing. So we have implemented that. We just didn't go over it. But yeah, that was yes. Any other questions?
You said that your system is semi-automatic. That was not explained.
Well, the semi-automatic portion, I'm sorry.
Why it is not fully automatic?
The semi-automatic portion of it is the fact that we will have the automatic scoring for the Cornhole and not for the aces. The issue that we had, we couldn't figure out a way to automatically score if a bag just landed on the board. That was portable. We did look into some ways to use like Connects, like if people are familiar with Xbox Connect, or bowling alleys actually use, we looked into that, they use like a camera detection method. The problem with that is you'd have to have an additional luggage to carry around to set up some sort of unit to view the box and bring in that data and process the visuals of that. So we thought it was, in order to accomplish it in our single semester and within our price range, it was best that we use just the semi-automatic scoring and use push buttons along with that.
I understood the logic of your pressure thing, but then when it comes to photo diodes or anything related to light, would it have been possible to still use that option in the design by changing the characteristic of the light for the 2 teams, or it would be completely impossible to implement that?
To be honest with you, that's not something that I did a whole lot of research into. I could look into that and get back with you. I'm not entirely sure if that would be a possibility for our system or not. I'd have to look into it.
Yeah, the reason I asked that is because I'm just eager to know whether that brings down the cost or that actually pushes the cost down if you implemented that approach. Then you mentioned the frequency of 13.56 megahertz, right? So how are you distinguishing the 2 teams? What characteristic of the RFID communication is used to distinguish team A from team B?
The characteristic is the tag has a unique identifier on it that's in form of like a hex code. So when the tag passes the sensor picks up that unique identifier. So each card, for instance, this is the not the hex value, but would be just the normal mathematical value. This card has a value of 181 for its first byte. This card has a value of 20. So that's what we implemented in our code. When we swipe this, there's a line of hex that comes through. The first chunk that we're looking at is a value of 181, and the opposing team has a value of 20 on their hex code. So each one's got their own line of hex that uniquely identifies it. And we have more tags, we just didn't bring them. And each one of those tags is going to have their own unique identifier. And the only reason we brought up the 13.56 megahertz, I guess, was the fact that it's a little bit different than what we're used to seeing. I don't know if it's the standard or not, but most of the cards that I've seen have had 125. and not this 13. It just happened that the ones that we ordered are 13.56.
Now, if I throw it really like low and fast, and it slides up the board completely over the hole, flies off the bench, is your scanner going to pick that up as a
No, it's
hole?
that would be out of range. It's going to be set down enough so we'll have to fall in and more or less make contact with our ramp.
So the sensor will be like on the ground?
The sensor not on the ground. It's probably about 4 inches underneath the hole on the ramp. Yeah, you can see the ramps. It's going actually underneath
Okay.
that ramp. So it'll be it looks like 3.18 inches is what we got there. Is how far down it is, and the range on that is maybe 2 inches, I would say, about where you can swipe that tag and it'll see it.
Okay.
You have a question?
Now, for the temperature testing, what is the ranges you are using?
The range for temperature testing, we plan on going about 35 degrees. So we'll just put in a room, turn the AC up, and just cool it all down. Same with heating. We'll probably do about 100 degrees. Again, it's a fair weather game. We don't expect people to play this in the snow, nor do we expect them to actually play it outside in blazing heat. It's mainly, during the fall, end of summer, early spring, in those sports seasons for the most part.
Did you guys happen to look into how likely it is that some other communication device is on that same frequency in the area, or is that a pretty open frequency, the 13 megahertz?
I didn't look into that into much detail. My assumption would be that our sensor has such a small range.
Oh, so
Someone
it's
would have to, if there was something using that frequency, they'd have to put it into our hole, which would be quite a coincidence. So I'm not sure why they would do that, but that didn't seem like much of an issue to us based off how this is built. But that's a good thing to look into.
Since there's an app for everything, could there be an app to kind of manipulate the wirelessly or scoring system?
Yeah, you could. I guess there would be the possibility to design an app that would then communicate with the XPs, perhaps, or the Arduino itself. I mean, I don't know. Currently, right now, if there would be one written to communicate
But
with
the
the
stakes
Arduino.
are not that high, right? I mean, so
Yeah. Who knows? They have big tournaments. There's a professional
They
league
do?
for this. There's a professional cornhole league that seems like it's pretty big. They got videos of people online. It's pretty intense. But for the average user, probably not.
From your presentation, just as a comparison, the electronic or the coding design was not very obvious. So can you maybe just briefly explain that what are the design aspects that you considered on the side of the electronics and coding versus the mechanical part? The mechanical part was well presented with the pictures and explained, right? So
Okay, like each part of our system currently, you mean?
yeah.
Like
So
you see the-
what are the design aspects? I mean, I don't want the specifics, but at least in general, what were your guidelines for the design?
In terms of the electrical components, what we were looking for and what we were trying to get. When we were initially looking into this,
It could be cost analysis. It could, so it could be a design based on any constraints. But what were your constraints? As an example, sensitivity of the sensors. or
Right.
Really, what were the electronic aspects that were
like
considered?
like you said, cost was a main constraint. There's some RFID equipment out there. We had to basically go out and get cheaper RFID sensor. There's some really expensive ones out there where you can actually manipulate the range that it can sense objects, and we could have gotten something like that, and it would have made a lot more accurate of a system. But with that cost constraint, we had to deal with, I guess, the money we had available. Same thing for the control device, and a lot of time constraints, I would say, as well. Having the ability to integrate all these things, it's usually not a very simple task to go and get an RFID or an LCD, or at least for us to get them all to integrate effectively with the control device in a short amount of time. So we really looked into things that would be effective for us. We could efficiently put them together and get it to work in a timely manner.
And what do you imagine the total price point of the entire system would be?
I think that depends on whether are we looking at what it would cost us, or if this was something that could be like mass produced, how cheap could we get it on the market?
Probably for the market.
I think we could really do this pretty cheap. Boards don't cost much to make. And the markup on some of these boards that we looked online, they're selling boards for $250. I think if we mass produce this thing, we could absolutely get it under $250, especially if we had more time to look at the integration process. We might have spent a little bit more money on certain things to integrate our wireless unit easier with our control device. We could buy cheaper items and figure out how to effectively integrate them if we had enough time to do that. We could get this system for under $250, I'm sure. And then you'd have you'd be able to have a electronic scoring system for as much or cheaper than a cornhole board that they have priced on the Professional Cornhole Association's website.
But what did it cost you to make it?
Our prototype cost was just under $225, I believe. So again, it's expensive, but we're buying each piece individually, marked up in Radio Shack and whatnot. So it's not like we're getting mass bulk discounts.
Now, as to weather testing, unless you are using industry grade electronic circuits like 5400 series for TTL, for instance, it wouldn't be fair to subject your hobbyist equipment to extreme weather temperatures or rain or this and that, because it's not intended for that purpose, right?
Correct. But we're still going to test. We're still going to try and get water on the board itself and make sure that when if you were to say it would start raining while you're playing, you should be able to just pick it up and be able to put it away just as you would if it would start raining normally. And it shouldn't have no rain should get in on the system at all.
What are the expected limitations of your?
Please answer that question briefly, because we have to switch to the next team in 3 minutes.
Can you repeat your question, please?
What are the limitations?
The main limitation, I think, would be the fact that we didn't have the money or the ability to make it portable enough to do a fully automatic scoring system. I think that would be the best way to go about this. If you could fully automate it and take the players' minds fully away from keeping track of the score, because they still have to go down and push a push button, which is still going to have the score displayed. It's still going to make their lives a lot easier, but it's time.
Thank you.
I'm getting
Great.
a signal from the back.
Thanks for
All
your
right,
time.
thank you guys.